An anti-tie-down circuit is a crucial safety mechanism implemented in electronic devices. Its primary function is to prevent a device from inadvertently activating if it experiences a sudden impact, such as being dropped or subjected to an abrupt force. This safety feature is achieved through the detection of rapid alterations in the power supply voltage. Should such a voltage fluctuation occur, the anti-tie-down circuit immediately responds by interrupting the power supply to the device. This action is vital in averting the device from initiating unexpectedly, which could potentially lead to damage to the device itself or, more seriously, cause injury to individuals in proximity. Understanding the intricacies of how an anti-tie-down circuit operates necessitates exploring several key aspects. Firstly, the purpose and functionality of the circuit. Secondly, the detection methods employed for voltage changes. Thirdly, the power cutoff mechanism. Fourthly, the advantages of implementing such a circuit. And fifthly, real-world applications. Firstly, the purpose and functionality of the anti-tie-down circuit. The core purpose is to safeguard against unintended activation. Imagine a scenario where a power tool is accidentally dropped. Without an anti-tie-down circuit, the impact could trigger the power switch, causing the tool to start running unexpectedly. This could lead to a dangerous situation, potentially resulting in injury. The anti-tie-down circuit acts as a safeguard, ensuring that the device only powers on when a deliberate and sustained action is taken to activate it. This is achieved by continuously monitoring the power supply voltage for any sudden anomalies. The circuit is designed to differentiate between a deliberate power-on sequence and a power surge caused by an external force. In the event of a sudden voltage change indicative of an accidental impact, the circuit immediately disconnects the power supply, preventing the device from starting up. Secondly, the detection methods employed for voltage changes. The detection of sudden voltage changes is a critical aspect of anti-tie-down circuit operation. There are several methods used to achieve this, primarily involving the use of voltage sensors and comparators. A voltage sensor is a component that accurately measures the voltage level of the power supply. This sensor provides a real-time reading of the voltage, which is then fed into a comparator circuit. A comparator circuit compares the measured voltage against a predetermined threshold voltage. This threshold voltage represents the normal operating voltage of the device. If the measured voltage deviates significantly from the threshold voltage, it indicates a potential accidental impact. The comparator circuit is designed to respond rapidly to these voltage deviations. When a sudden voltage change is detected, the comparator triggers a signal that activates the power cutoff mechanism. The speed of the comparator is crucial, as it needs to respond quickly enough to prevent the device from powering on before the cutoff mechanism is fully engaged. Some advanced anti-tie-down circuits may employ more sophisticated detection methods, such as analyzing the rate of change of the voltage. This allows the circuit to differentiate between a slow, deliberate voltage increase as would occur when intentionally powering on the device and a rapid voltage spike as would occur during an accidental impact. Thirdly, the power cutoff mechanism. The power cutoff mechanism is responsible for physically disconnecting the power supply to the device when a sudden voltage change is detected. This mechanism typically involves the use of a switch, such as a transistor or a relay. When the comparator circuit detects a voltage anomaly, it sends a signal to the switch, causing it to open. This opening of the switch breaks the electrical connection between the power supply and the device, effectively cutting off the power. The choice of switch depends on several factors, including the voltage and current requirements of the device, as well as the desired speed of the cutoff mechanism. Transistors are often used in low-power applications due to their fast switching speeds, while relays are more suitable for high-power applications. In some cases, the power cutoff mechanism may also include additional components, such as a fuse or a circuit breaker. These components provide additional protection against overcurrent and short circuits, further enhancing the safety of the device. The design of the power cutoff mechanism is crucial to ensure that it can reliably interrupt the power supply in the event of an accidental impact. The switch must be able to handle the full load current of the device without failing, and it must be able to open quickly enough to prevent the device from powering on. Fourthly, the advantages of implementing such a circuit. The implementation of an anti-tie-down circuit offers several significant advantages, primarily centered around enhancing safety and preventing damage. The most important advantage is the prevention of accidental activation. This is especially crucial for devices that could cause injury if they were to start up unexpectedly. Power tools, machinery, and other potentially hazardous equipment benefit greatly from the safety feature. By preventing accidental activation, the anti-tie-down circuit helps to protect users from potential harm. Another advantage is the protection of the device itself. A sudden impact can sometimes cause damage to the internal components of an electronic device. By cutting off the power supply immediately after an impact, the anti-tie-down circuit can help to prevent this damage. This can extend the lifespan of the device and reduce the need for repairs. In addition to safety and damage prevention, anti-tie-down circuits can also improve the reliability of electronic devices. By preventing unintended operation, the circuit helps to ensure that the device only functions when it is supposed to. This can reduce the likelihood of malfunctions and improve the overall performance of the device. Finally, the use of anti-tie-down circuits can contribute to compliance with safety standards and regulations. Many industries have specific requirements for safety features in electronic devices, and the implementation of an anti-tie-down circuit can help to meet these requirements. Fifthly, real-world applications. Anti-tie-down circuits are widely used in a variety of electronic devices and applications. They are particularly common in power tools such as drills, saws, and grinders. These tools can be dangerous if they were to start up unexpectedly, so anti-tie-down circuits are essential for ensuring user safety. Anti-tie-down circuits are also used in machinery and industrial equipment. These machines often operate at high speeds and can cause serious injury if they were to malfunction. The use of anti-tie-down circuits helps to prevent accidental activation and reduce the risk of accidents. In addition to power tools and machinery, anti-tie-down circuits are also used in consumer electronics such as smartphones, tablets, and laptops. While these devices are not typically considered to be hazardous, they can still be damaged by a sudden impact. The anti-tie-down circuit can help to protect the device from damage and prevent unintended operation. Another important application of anti-tie-down circuits is in automotive electronics. Modern vehicles contain a wide range of electronic systems, including engine control units, braking systems, and airbag systems. These systems must be reliable and safe, and anti-tie-down circuits play a critical role in ensuring their proper operation. For example, an anti-tie-down circuit in an airbag system can help to prevent the airbag from deploying accidentally, which could cause injury to the vehicle occupant. Furthermore, an anti-tie-down circuit can be integrated into safety interlock systems. These systems are designed to prevent machinery from operating unless certain safety conditions are met, such as the presence of a guard or the engagement of a safety switch. The anti-tie-down circuit ensures that the machinery cannot be started simply by overriding the safety interlock, providing an additional layer of protection. In the context of robotics, anti-tie-down circuits are essential for preventing robots from performing unintended actions that could cause harm to humans or damage to the environment. These circuits ensure that the robot only operates under controlled conditions and can be quickly shut down in case of an emergency. In summary, the anti-tie-down circuit is a fundamental safety feature in electronic devices designed to prevent accidental activation due to sudden force. It functions by detecting changes in the power supply voltage and cutting off power to the device. The circuit's operation involves voltage sensors, comparators, and a power cut-off mechanism. Its advantages include preventing accidental activation, protecting the device from damage, improving reliability, and aiding compliance with safety standards. Real-world applications span power tools, machinery, consumer electronics, automotive systems, safety interlock systems, and robotics. Understanding the principles and applications of anti-tie-down circuits is essential for engineers and technicians involved in the design, maintenance, and operation of electronic equipment.